Okay, and let's get started. Sorry for the start. And okay, let's come back. And today we are going to start into chapter 5, and it's discrete-time Fourier transform. Okay, and let's start with this picture, and this is a picture of the Fourier transform family. And you can see that we have taught three of the three of the four possible Fourier transform, and we have seen that for periodic signal we have the Fourier series and discrete-time Fourier series. Okay, those was taught in chapter 3, where the signal is periodic, and then we have those Fourier series coefficient AK, and for for non-periodic signal, then we had the Fourier transform in chapter 4, and in chapter 5 we'll talk about the discrete counterpart of Fourier transform. That will be the discrete-time Fourier transform. Okay, and so you can see that we have taught a lot of things that are similar to this discrete-time Fourier transform. So this chapter will be really easy because this is basically the counterpart of chapter 4, but now with discrete-time input. But here there is something I want to emphasize. That's something about notation. Okay, so what we taught today in this chapter is discrete-time Fourier transform. And there is something called discrete Fourier transform. That actually means the discrete-time Fourier series. Okay, and so that's just some notation to make sure that you don't look at things wrong. So this is discrete Fourier transform actually means the discrete-time Fourier series we talked about in chapter 3. It's because this thing is called discrete Fourier transform because both its time domain and the frequency domain signal is discrete, and so in a lot of books it's also called, and other places it's also called discrete Fourier transform, and people even have equivalent for it. You will call DFT. Sorry, this is hard. Okay, yeah. So the discrete Fourier transform is also called DFT, and it actually means the discrete-time Fourier series. And what we told about today is discrete-time Fourier transform. There's the HR time, and it's a different thing. Okay, and here is a better comparison of all the Fourier transform family we have. Sorry, this is pretty bad. Let me see if I try this thing will be better. Let's try this. Does the HDMI here work better? No. How about this? Somewhat. Let me try. Okay. Sorry about the technical difficulty. Okay, should be working now. Yeah, and here is a table to compare those for Fourier transform. And so chapter 3 we have this continuous time Fourier series. You change from x of t to ak, and then we also in chapter 3 we'll talk about this discrete time Fourier series where we have x of n go to ak, and we have seen that the x of n and ak are very symmetric because both of them are periodic with a period big N. And then in chapter 4 we talk about Fourier transform where our x of t is not periodic anymore. Then we transform this to this big S over j omega is also not periodic. And in this chapter we'll talk about this discrete time Fourier transform where we have a discrete signal that's aperiodic in the time domain, and we'll transform it to some frequency domain signal, and it will be called the big S of e to the j omega. And okay, And yeah, so that's a bit of skimming ahead of what we are going to get today. And then the difference from this to chapter 4 is that just like the difference between the continuous time and the discrete time Fourier series, now in the frequency domain we'll get the frequency domain will be periodic. Okay. And indeed we'll see that the frequency domain signal is periodic with a 2 pi period. Just because the time domain signal is discrete. It's like here in chapter in the discrete time Fourier series, we also get that the Fourier series coefficient are periodic because the time domain signal is discrete. Okay, and yeah, here is a quick table of what we're going to see, and you see it's very similar to chapter 4. We have the basics of the Fourier transform, and then we have properties, and we'll talk about how to use it to solve some difference equations. Okay. And let's start with the derivation of the discrete time Fourier transform. Is very similar to chapter 2. Derivation is the same idea. So we start with some aperiodic signal. So we have some aperiodic signal x of n here. We assume it has some finite duration from minus n1 to n2. And so we want to use the discrete Fourier series to derive our discrete Fourier transform. So what happens is we keep copy pasting this signal and to get a periodic signal. So we choose some period big enough to contain this minus n1 to n2, and we just keep repeating this signal. So we get some x tilde of n. That's just repeating this x of n for every big n. Okay, so it looks like this. So and because x tilde of n is now a periodic signal, then by the chapter 3 result, we can have the Fourier series representation equations for x tilde of n. So x tilde of n will be the summation ak e to the jk omega n, and ak equal to 1 over n, summation n x tilde of n e to the minus jk omega n. Okay. This is the Fourier series representation of this periodic signal x tilde of n. Okay. And then we look at this ak as a function of x tilde of n, and then we do the same approximation, not approximation, sorry, and same manipulation as in chapter 4, where we see that so this summation summation bracket n is summing over some interval of length big N. And then a good interval to pick is something like including this minus n1 to n2. And so this reasoning is that we are summing x tilde of n from minus n1 to n2. And and the last thing are summing x of n from minus n1 to n2. Because x tilde of n and x of n are same between minus n1 to n2. And now you are summing over x of n, then it's summing from minus n1 to n2 is the same as summing over the whole line of n. Okay, so you can also, if you change x tilde of n to x of n, then you can also change the limit of summation from minus infinity to plus infinity. So you see that ak can be written as x of n. Okay, okay, so ak as x of n, and now we try to write ak as some envelope function is big X of e to the j omega. And now we just give a definition here. So big X of e to the j omega is the summation x over e to the minus omega n. Okay, and the idea here is kind of you look at the ak and you see how it depends on k is you have how it depends on k, the n is you only depend on this k omega 0. Okay, so you have k omega 0. So if you combine k omega 0 as omega, then your ak can be written as this x of e to the j omega taken value at omega equal to k omega 0. Okay, and also divide by 1 over n. Okay. So this is similar to the envelope function we see in chapter 4. We think if as omega goes to 0, this big X will not change. It will have the same envelope function. You're just sampling over this envelope function more and more frequently. Okay. And algebraically, you just see that the ak can be written as this big X over e to the j omega. This is function of big X, and the taking point at omega equal to k omega 0. Okay, it's just algebraically true. Okay, and now we think about what happens when you take n go to infinity and omega 0 go to 0. Okay, and so we sub this ak back into our x tilde oven. Okay. And we see that the x tilde oven, we had this synthesis equation for x tilde oven, and the x tilde oven is summation ak e to the jk omega naught n. Okay, and then we write down this ak, this summation k, and 1 ak is just this 1 big X, and then e to the jk omega naught n. Okay. Then we also do a further change, is we change this 1/n to be omega naught over 2 pi, just because omega naught equal to 2 pi. Then this x tilde oven, now we return it in a very interesting form. It's 1/2 pi and summation k e to the big X of e to the jk omega naught times e to the jk omega naught n and times omega naught. And so we see how this depends on omega naught. We see that then we have this part, this big X times e to the jk omega naught n part. It only depends on k omega naught. And then we are summing over this thing times omega naught. And we can think this as actually integral as omega naught go to 0, because you look at this picture where you have a function that's height is big X e to the j omega n, and then those two values, this big X of e to the jk omega naught and e to the jk omega naught n, can be viewed as the height of this function taking value at k omega naught. Okay, so like this point. So this function taking value at k omega naught, and then you times then multiply by omega naught is like this area of this rectangle, where height is this function taking at k omega naught and width is omega naught. Okay, and then you're summing over this k from 0 to n is summing over k from 0 to n is basically summing over this whole bunch of this rectangle, where k omega naught goes from 0 to 2 pi or from minus pi to pi. Okay, so summing over k with with the interval of big N is the same as summing over this n omega naught from interval of 2 pi. Okay, and so you are just summing over these rectangles, with interval of 2 pi, and as our usual calculus argument, we think as omega naught go to 0, the area of these rectangles will converge to the area of this curve, the area under this curve. Okay, and so as omega naught goes to 0, we turn this summation into integral, and so we think this x tilde of n equal to this 1/2 pi, and the integration of once again we say this k range over big N become n omega naught. I should not say k omega naught, okay, because n omega naught equal to 2 pi, so a range over big N become k omega naught range over 2 pi, and then we have those two functions, so big S of e to the j omega and e to the j omega, then the omega naught become d omega. Okay, and so we do this derivation, so we think that as omega has n go to infinity or omega naught go to 0, I guess I should return that here. So what happened here is we think what happened when n go to infinity and omega naught go to 0. Maybe I should write as this. So as n go to infinity, omega naught will go to 0. And what happened is we can get equation for x tilde of n as integral big X. And also we think as n go to infinity, x tilde of n will go to x of n. So the argument was that you look at those two signals, and as big N goes to infinity, those repeated part goes further and further away, and the signal will look more and more like each other. Okay, and yeah. So we have this kind of hand-waving argument, so that as n go to infinity, x tilde of n go to x of n, and so we just have x of n as a function of a big X like this. X of n equal to 1 over 2 pi integration over range over 2 pi big X over e to the j omega, e to the j omega and d omega. Okay, and yeah, and because those two functions are this x of e to the j omega and e to the j omega are periodic with period 2 pi, then the interval can be taken at the integration interval can be any interval of length 2 pi. And then we got our two most important equations of this chapter. That's the Fourier transform equation and the inverse Fourier transform equation for discrete-time Fourier transform. Okay. And yeah, let's look at that here. So, and read through that. So, since this equation, x of n or the inverse Fourier transform equation, x of n equal to 1 over 2 pi integration over 2 pi x of e to the j omega times e to the j omega n d omega. And then the Fourier transform equation, big X of e to the j omega equal to summation n from minus infinity to plus infinity, x of n e to the minus j omega n. And you see they are very similar to a continuous time Fourier transform, basically the same, except that well, obviously the integration becomes summation, and also the integration range was infinite here, but now it's periodic. So, but now big X was periodic, so integration range becomes 2 pi here. Okay, you see that very similar to continuous time case. Okay, and as we say, this integration 2 pi range can be sorry, yeah, try to hold this together. Okay, this integration 2 pi range can be any interval 2 pi, and for example, you can take 0 from 2 pi or minus pi to pi. Okay, and yeah, just like in chapter 4, this big X over e to the j omega is called a spectrum of x of n, or called a frequency domain signal, because we think big X and x are basically the same signal. We are just looking at it at different angles, and so x of n is the time domain signal, and big X of e to the j omega is the frequency domain signal. And let's keep a bit of a note, I guess, before I go here. Any questions so far about derivation? It should be very similar to chapter 4. People okay? Okay, and yeah, so that's a derivation. Derivation you can kind of forget, although it's nice to remember. But the two equation is what you should remember. You should memorize it. Yeah, although different books will have different notation, but you should remember the general form of them. Okay, and some note. Okay, so some note more about the discrete time. Okay. And so first is, well, obviously we derive the discrete-time Fourier transform from the discrete-time Fourier series, and taking this big N go to infinity. Okay, and the important thing we keep saying is that the spectrum, this big S of e to the j omega, always has a period 2 pi. Okay, it's always a periodic function with a period 2 pi. Okay, and it can be easily proved by, I guess, one of the equation. You can take the analysis equation here, and see what happens when you change omega to omega plus 2 pi. So big X of e to the j omega plus 2 pi, and so you get HR 2 pi from on this e to the minus j omega n. Okay, and so what you get is you get HR e to the minus j 2 pi n. Yeah, e to the minus j 2 pi, and but you know, but because n is an integer, and you know e to the 2 pi j is 1, so this is just 1 to the minus n, and it's always 1. Okay, and yeah, so here we prove that big X, when you change omega to from omega to omega plus 2 pi, big X doesn't change. Okay, and yeah. And Okay, yeah, so this is periodicity of big X. And also one thing about this notation, you see that in chapter 4 we say this frequency domain signal is big S over J omega, and now we say the frequency domain signal is big S of e to J omega. You might think, why do we have this funny notation? Why don't we just say omega here or J omega here? Okay, and the reason we don't say J omega here will be clear later, but the reason we say the reason we have HRJ here will be clear later, but the reason we have HY exponential here, we can kind of say is because exactly because of this period of 2 pi. Because you see that e to the j omega equal to e to the j omega plus 2 pi. This is just an equation. This is also true, always true. And yeah, so you see that this notation will fit nicely with this periodicity of 2 pi, because you see that you increase omega by 2 pi. This function should not change, so why not just put something that doesn't change by 2 pi inside? You put this as a function where e to the j omega. And e to the j omega doesn't change when you change omega, so you increase omega by 2 pi anyway. Okay, so this notation will make this periodicity very obvious. Okay, and yeah, any questions so far? So yeah, anyway, here what we want to say is this function, as a function of omega, it has a period 2 pi. Okay. And then we need to talk about low frequency and high frequency signal of discrete signal, and we kind of talked this before. So low frequency signal will be so low frequency signal will be a signal that's mostly on the same side. Okay. So the low frequency signal for discrete signal will kind of look like this. No, it's not periodic. Okay, so it's maybe you have a peak somewhere, and in the frequency domain, the signal will peak around 0 and 2 pi and all those multiple pi. And the high frequency signal might look a lot like a low frequency signal, but it will have this plus minus structure. Okay. And yeah, so high frequency in the discrete case means that you keep flipping between plus and minus, and in the frequency domain, the signal will concentrate around those odd multiple of pi. So like pi minus pi, 3 pi minus 3 pi, etc. Okay. And let's see a case very quickly, immediately, to see what the low frequency and the high frequency signal in discrete time case look like. Okay, and so our signal is x of n equal to, so this a to the n u of n, and with absolute value of a less than 1, but let's say a is for now it's a complex number. Okay, so this is very similar to the first example in chapter 4 too. Also, remember in chapter 4 we have e to the minus at u of t. Okay, and now this is also an exponential decay signal, and starting at n equal to 0. Okay, and we have a bit of a sketch of the signal when a is a real number, so a is greater than 0, then you kind of have this exponential decay with a positive, so it's just decaying because the absolute value of a is less than 1, so it's like the decaying signal started at n equal to 0. And when a is less than 0, then you have this up-down decaying signal. Okay, so the absolute value of a is still exponential decay, but because a has a minus sign, so the signal will flip up-down. Okay, and you can think this is kind of a low frequency signal, and this is a high frequency signal, because the signal is keep oscillating up-down. Okay, and anyway, we can just algebraically calculate the Fourier transform of this signal without concerning whether a is positive or negative. We can just think a is any complex value and do the analysis equation. Okay, and big X of e to the j omega should be the summation x of n, so a to the n u of n times e to the minus j omega n. Okay, so summation n from minus infinity to plus infinity, and then this u of n will cut off this thing from n to from 0, and then you see all the other thing is actually a geometric series. So you have a over n e to the minus j omega n, and that's a times e to the minus j omega to n. So you just have a summation of a geometric series, and now this absolute value of a less than 1 is important because you want this series, the summation of this series to converge. So you use this, this condition here to make sure the summation of the series converge, and you can use the geometric series formula to see this is just 1 over 1 minus this number here. Okay, 1 over 1 minus r, where r is the ratio here. So and it's a e to the minus j omega. Okay, and we can plot, try to plot this result in terms of a greater than 0 or a less than 0. Okay, and we can kind of think about what's the absolute value of this thing. Okay, and so this thing. Let's first look at, so this is a quite complicated formula, but let's look at what's 1 minus a e to the minus j omega, and so you can think about, well, a is a complex value, so you have something on complex plane. So you can think about this, so there is a 1 part and a e to the minus j omega part. So a times e to the minus j omega will be something on this circle with radius a. Okay, so we draw a circle on complex plane with a radius that's absolute value of a, and then you see this e to the minus j omega will change the position of this, change your position on this circle. Okay, so when omega increase, you kind of walk on this circle clockwise, because you increase omega, then you decrease the phase here. Okay. And what's 1 minus a e to the minus j omega is the distance between this 1 and the point you have on this circle, so kind of this black line. Okay, so maybe your a e to the minus j omega is here. Okay, and then obviously when the distance is smaller, then your big X absolute value is higher. Okay, and the distance is larger, then your big X is smaller. Okay, and the distance is the smallest when your a e to the minus j omega is very close to 1. Okay, so there are 2 points. So the closest point is here. This is when your big X is largest, and the furthest point here. So this is when your big X is small. Okay. So this point is a big X small, and this point is big X large. Okay, and big X large. Okay, and then you can see that when your a is positive and negative, then you have the different omega where big X is larger and small. Okay, and when a is positive, then you start working on and omega equals 0, you start on this big X is large point. I should say the absolute value of big X, because big X is actually a complex value. Okay, and so a is positive, then you start with this large point, and when you increase your omega by pi, then you walk to this big X small part, and you keep increasing omega, then you walk back to this large point, and so you get this big X graph like this. You start with big X large, and the largest one is 1 over 1 minus a, and then you walk to the smallest one, and it's 1 over 1 plus a. Okay, and then omega changes to 2 pi, you go back to the largest point. Okay, and on the other hand, when a is negative, you start on this point. Okay, you start with phase being pi, and so you start with big X small point, and you increase omega pi, you go to this big X large point, and you walk back to this big X small point. Okay, and so your big X graph look like this, and then remember back to what we have here, and we see that indeed when A is greater than 0, we have this lower frequency signal, and when A is less than 0, then when A is less than 0, then you have this high frequency signal centered around pi. Okay. And also you can draw the phase of big X here. And we don't do further analysis, but you can derive these two pictures from this equation. Okay. Any questions so far? Yeah. And it's also nice to remember this equation because we'll use it to, just like in the continuous sum case, because we will use this to solve our difference equation. Okay. And yeah, so that's our first example of a discrete-time Fourier transform. It's nice to memorize the result. X of n equal to a to the n u of n, and big X equal to 1 over 1 minus a e to the minus j omega. Okay. And then the second equation, we have very similar to the first equation, and indeed you can even use some symmetry to derive this result. But here we do brute force calculation, okay? And here x of n equal to a absolute value of n. And skip ahead a little bit, we can see a signal is two-sided exponential decay. When here is when a is greater than 0, okay? And yeah, when a is greater than 0, you have this two-sided exponential decay. And once again, we have absolute value of a less than 1, okay? And big S of e to the j omega, we can once again just use brute force calculation. And so it's summation a absolute value of n e to the minus j omega n. And to break this absolute value, we just break n to be greater or equal to 0 and less than 0 part. And so on the greater than 0 part, we just have a of n, and when n less than 0, then we have a of minus n. Okay. And then the a of n part, once again, is a geometric series. We can write down. We see it's a geometric series, and we can write down its result just like previously. And for this n less than 0 part, we do a change of variable. We just change n to n equal to minus n, and this is summation n from 1 to infinity. And also a similar function a e to the j omega to the n. Okay. And yeah, so you sum over these two geometric series, and we skip the algebra, you get this result 1 minus a squared over 1 minus 2a, cosine omega plus a squared. Okay. And we see that when a is greater than 0, we have this signal. And now big X now is a real function, and it's a bit related to the symmetry property that we kind of see in chapter 4. It's because it's now a real and even function. X of n is now a real and even function, and then big X is also a real and even signal, real and even function. Yeah. And anyway, so that's big X now. And you see that when a is greater than 0, big S is centered around 0 and 2 pi, etc. It's a low frequency signal, and you can plot yourself that when a is less than 0, then big S will once again center around pi and minus pi, etc. Okay. And okay. And the next one, we go to our block wave signal example. Okay. And yeah. And our x of n is this block signal, so it's from minus n1 to n1. Okay. And and x of n will be big S or e to the j omega will be summation. This is summation from minus n1 to n1 e to the j omega n. Okay. Because the block signal just change your range of summation from minus n1 to n1. And we'll have to do the similar calculation in chapter 3, so we skip the calculation, and we see the result is sine over sine. So it's sine omega n1 plus 1 over 2 over sine omega over 2. Okay. Okay. And yeah, so it's similar to example 3.12, but just in the previous example we have basically omega equal to k omega 0, and but now we just have omega here, and but the signal is periodic with period 2 pi on omega. Okay. And yeah, as we say, we can see that in all our examples the output has a period of 2 pi. And this is a property that is true for all big X for the discrete time signal. Okay. And then we have a bit more time. Let's see, we have 10 more minutes. So let's see whether we can finish the convergence. Okay. And then we now think about the convergence issue associated with the discrete Fourier transform. And once again, those two are discrete Fourier transform equation. X over n is its integral, big X is its summation. Okay, and yeah, and yeah. So here we also need to be careful about the convergence, and basically because we are summing over. Okay, and now the convergence is be better on this equation because the integration is over a finite interval, but the summation here is still infinite, and it's very likely to diverge. Okay, and yeah, so in particular, the summation over infinite range might not converge. Okay, and but here once again we have some condition that we claim that if it is satisfied, then our series will always converge. Okay, and the condition here is that our x over n should be absolutely summable. Okay, so absolute value of x over n summation from n infinity plus infinity should be a finite value. Okay, or it has a finite energy. Okay. And yeah, here we don't have much proof. We just claim that this is true. Okay. And I guess one of the motivation here is that you can see this is kind of similar to the Dirichlet condition we keep talking about. We say Dirichlet condition is your signal needs to be absolutely integrable, and but Dirichlet condition will also have 2 and 3, saying that you should not have too much minima and maxima and too much discontinuity. But now x over n is a discrete time signal, so there is no way it has too many minima, maxima and minima, or too many discontinuity, and so we only have absolutely summable here. And finite energy is a condition that very similar we had similarly before. Okay, and also equation for 5.8 we say that EOJ converge just because we have a finite interval. Okay, and let's see some example of the convergence. So x over n equal to delta of n. Okay, and delta of n now is a very convergent signal. And we can calculate that big X over e to a j omega equal to 1 because yeah, because you sum over this thing, and then you see that there is 1 everywhere because the delta of n will say the n equal to 0 here. Okay, and then you try to have inverse Fourier transform on this thing, and you see that you will converge back nicely. Okay. Okay. Yeah. You see that so here this example is a bit funny. So this example is showing that there is no Gibbs phenomenon, basically showing that there is no Gibbs phenomena when you converge to a black wave signal in the discrete case. Okay, so we are seeing that this signal when you integration back to the discrete x over n, there is no Gibbs phenomena, and that makes sense because you are discrete time sampled here, and there is no place you can place the repose. And we're seeing this in a more extreme case. So x over n equal to delta of n, and big X equal to 1. and then you think about you integrate this big X back into some X hat from some finite range minus omega to omega and then equal to sine omega n over pi n, and and then you can see that you increase omega, but now you increase your W. So from minus W to W and sine Wn over pi n. And but the W you don't only need to go to infinity, you only need to go to minus pi to pi. And you see that as you increase W from this pi over 4 and 3 pi over 8 and pi over 2, 3 pi over 4, etc. You see your signal looks more and more like your delta of n. And indeed, when W equal to pi, you converge to delta of n exactly. And it has no Gibbs phenomena. Okay. And so block wave in the time domain will converge nicely to the to a discrete signal here. Okay, but but you can think about this thing. So kind of skip ahead to duality. Then you can think about this thing will have trouble in okay, let's try to say a bit of duality. But if you have a sync signal, so if you have like a periodic wave in the frequency domain, okay, and so you have a periodic wave in frequency domain, then you will have this discrete sample sync function in the time domain, and then you try to converge it back, and you can check whether you got a Gibbs phenomenon. That's a different thing. Okay. So the discrete Fourier transform is a bit funny because you don't have the time domain signal and the frequency domain signal are very different because the time domain signal is discrete time and the frequency domain signal is continuous time. And so it's kind of similar to the and later we'll see that it's actually due to the continuous time Fourier series. Okay. And where one of the signal is discrete and one of the signal is continuous but periodic. Okay. And so but anyway, when you try to convert integration back to the this discrete time domain signal, you see that there is no Gibbs phenomena because, well, there is no place you can place the repose of your Gibbs phenomena. Your signal is discrete time. Okay, so it has been a bit better convergence. Okay, and we have 5 minutes, so I don't think we have enough time to go this, but let's flash a little bit ahead. And so the next topic we'll talk about Fourier transform of a periodic signal, and it's kind of similar to the continuous time case. We say for periodic signal, we also want to get Fourier transform, and we'll get a whole bunch of delta functions. But also remember that our frequency domain signal is not periodic with period 2 pi, and so what we'll get is something like a linear combination of a whole bunch of impulse train. So because every impulse should be repeated every 2 pi, and so the Fourier transform result of a periodic signal is a whole bunch of impulse that repeat themselves every 2 pi. Okay, and and then we'll see the details of the algebra next time. Okay, so a small review. So here today we derive the discrete Fourier transform. Its equations are those two. X of x of n is from integration over period 2 pi of big X over big X, and big X is a summation of minus infinity to plus infinity of x over n. Okay, and I guess let's go back to a bit of a duality. Okay, and so this is what we do today, and so this is a discrete time counterpart of what we do in chapter 4, and later we see that this is actually due to what we talk very first is the discrete time continuous time Fourier series, where the time domain signal is continuous and the frequency domain signal is discrete. Okay, so you have a continuous but periodic here and discrete here. And in this chapter, we have a continuous here, we have a discrete here, and continuous but periodic with period 2 pi here. Yeah. And so duality actually due to the chapter 3, and it's quite interesting. Okay. And so that's for discrete time Fourier transform today, and we'll talk about periodicity and some properties next time. Okay. So see you next Monday. Okay.